of the micropollutants in high recovery reverse osmosis system. So let's talk about need for reverse osmosis in water use. So we have different water resources available, and each country, depending on their situation, they utilize different water resources. For example, in China, they have a high amount of the surface water or groundwater, so they can rely on more supply water or wastewater treatment. But for some country like the Middle East area, they rely on desalination because they don't have enough surface water sources. And with the climate change, the water sources is changing. So as you can see on the right figure, the desalination and water usage is increasing dramatically. And especially for the desalination, membrane-based desalination is the dominant right now. And then the thermal desalination is declining because of the energy usage. And let's talk about desalination and water reuse. For the desalination, as I mentioned, Middle East countries are focused more on the desalination, but seawater desalination demand is also increasing in non-traditional region. For example, Singapore, they focus on independent water security because they import water from Malaysia. In Australia, they experience big drought and like the flood. So they are even expanding their Sydney desalination plant. And Chile, they have a rising mining industry. For South Korea, actually, we also have abundant water resources, but because of the seasonal variation and climate change, they are installing new big desalination plant for the industrial development. And for China, industrial demands and droughts of that so that they are increasing their seawater desalination, especially in the northeast region of China. They have a factory and they need this SWR desalination for water supply. But the problem of the desalination is energy consumption. In 2019, I collected data and analyzed the energy consumption of the desalination plant. And at the time, the lowest desalination plant SEC was about 3.0 kilowatt hour per cubic meter. But after 6 years, we had an analysis again, and it shows that the energy consumption can be reached to 2.8 with the larger capacity and advanced membrane technologies. But still, its energy consumption is dramatically higher than surface water treatments, so that we can focus more on water reuse because they have a lower salinity, so the water treatment energy consumption can be lower. So when you see the graph, the Asia Pacific region or Middle East Africa country focus more on water reuse. So for example, for the Kuwait, they have a large water reuse plant and they utilize RO as the end step. And Singapore, as you well known, for new water, they utilize the RO and UV for utilized as a reuse purpose. And Australia, they also have it. And RO is actually eliminate organic micropollutants and suspended solid, and even the TDS, so they can be the promising solution for the water reuse. And when I see the description of REMP, I was a little bit curious and nervous because micropollutant is not my research. But still, when I see the description, surface water or municipal wastewater treatment can be my research. At the same time, for the advanced water treatment, like the technologies, I focus on the high recovery RO. So this can be my research, and some low recoverable rate and low permeances and fouling, that can be my work scope. So my talk will focus on high recovery RO for water reuse, and my research might be limited for the micropollutant effects, but at least I can suggest some point for consideration altogether because we have different expertise like membrane, like the synthesization and processes. So I will share my research and share some questions that we can think of together for the micropollutant removal in high recovery reverse osmosis. So I will explain about the BWR configuration first. For the water reuse, we are using brackish water reverse osmosis. So reverse osmosis, as you know, they might have a lower recovery rate. So single stage or single pass is general like the configuration, but because of their low recovery rate, they install additional stage like the 2-stage. So for the low saline water, they install without the interboost pump so that they can increase the water recovery. For the higher salinity water, they utilize the inner booster pump inside so that they can boost water production in the later stage. or more developed, like the BWR configuration, they utilize split partial concept for the second stage. So they are retreating the relatively high saline permeate again back to the feed water so that they can keep the quality and also quantity. And for further expansion, they can utilize the multi-stage or cascade design so that they can increase the recovery up to 98%. So some desalination plant adopt this design as their second pass design so that they can increase the water production. So likewise, for the water reuse or brackish water reverse osmosis, high recovery is needed. At the same time, as you can see, there is a complex design for the BWRO. So there should be some simplified BWRO processes. So the current research focus on like the semi-batch or batch design. So multi-stage RO utilize additional like the stage for the RO, but this will occupy larger spaces and capital costs. So they are utilizing the concentrate again back to the feed and increase the recovery with the compact side. And recent study focus on batch reverse osmosis as well, but that one is a little bit difficult to apply in real cases because there are some like the pressure control point. So semi-batch RO without this like the batch system is utilized much in the industry and recent academia. And the feature of this semi-batch RO is they have a plug flow or closed circuit mode, which means they are discharging and concentration process at the same time. And many field and modeling study has been conducted for the semi-batch RO, but what I realized is their focus and their like the characteristics can be a little bit different. So for the field study, like for example, DuPont, they have their own semi-batch RO design and their focus, which called CCRO, and they have a pilot scale application a lot for the brackish water reverse osmosis condition. But for the modeling study in academia, they focus more on SCC. So energy consumption is their target for study. But as you can see, practical conditions were not considered in the modeling studies in academia. And they don't consider its capacity, and even the recovery is extremely higher compared to their feed condition. And also, they don't consider water flux, which is a very critical parameter for this plant design. And even for the pump efficiency is extremely high, so that they claim the semi-batch RO is extremely low energy consumption RO configuration, but actually it is not. This is very different from the reality. And also the permeate TDS in real condition is very important, but in the modeling condition, they don't consider it and ignore it. So that's the differences in the field and modeling study. And let's think about what will be the potential consideration for the micropollutant removal. So I plotted some like the data for the practical energy consumption, like the range and some recovery, target recovery based on TDS condition. And also plotted some like the concentration changes depending on the concentration side and in the replenish side. But as you can see, the permeate can be increased during the concentration and then they will be lower during the discharge. So which means that there is an unstable permeate quality if there is no buffer tank beside. So with the higher permeate, like the production in the concentration side, this might be the potential problem for the micropollutant permeation during the concentration. So this point can be considered. And then after summarizing all the field and academic studies, we can conclude 4 directions for the semi-batch reverse osmosis. First thing is we need to focus on realistic SCC evaluation because that's their consideration. And permeate quality is often neglected. But as we focus on the micropollutant removal, this should be focused as well. And micro and membrane fouling and scaling, and this can be also the interest, and practical design is also an interest. So I conduct multiple study after that, and I will share more like the questions or some finding about the micropollutant removal. So the first approach that I did with the company is to develop some semi-batch process for removing the fouling, like removing the fouling propensity. So for the conventional semi-batch, they have recycled processes, but when the concentrate and feed is met, there will be some energy losses. So this will increase the energy consumption. That's why we are utilizing the jet pump, which will supply the feed and concentrate in the same direction so that we can reduce the energy losses. And for the RO design, they utilize the two-stage so that we can distribute the flux more evenly, because the front element relatively has high water flux, which will increase the fouling formation. But with the two-stage design, they can lower the flux and evenly distribute the flux. And at the same time, they can use the flow reverser technology, which can change the direction of the feed so that they can evenly utilize the membrane and expand the RO membrane, like the lifespan. So that was the approach to develop the fouling mitigating, the high recovery reverse osmosis, and we tested in the wastewater treatment plant in 2023 to 2024. So we supply the effluent from the wastewater treatment plant, and we utilize the tertiary effluent as a feed condition, and we use the UF for the pre-treatment, and then utilize this high recovery RO for the water production. And I can suggest some point. So what we realized is the wastewater treatment plant, they don't consider micropollutant, but they focus more on the TDS or other organic compound. So micropollutant might not be interest of the wastewater treatment operator. And for the high recovery or reverse osmosis, their focus is more on energy consumption or recovery rather than those micropollutant removal. So there's a limited attention on micropollutant. Even for the operation of this, like the pilot plant, because they have a high fouling resistant ability, they exhibit relatively stable energy consumption, like 0.71. And then they also have a relatively stable permeate production, like the 33 microsiemens per centimeter as a feed condition. But we only monitor the conductivity as a real-time monitoring indicator. For indicating those micropollutants, they need a lab experiment in addition. So that's the limitation for the real-time analysis of the micropollutant. So that will be the potential consideration point for the high recovery reverse osmosis. And for the permeate production, as you can see, as I had an analysis before, there is a concentration increasing during the concentration processes. So this will potentially increase the micropollutant permeation during the concentration point. But those concentration point is missing in real application. And with the successful high recovery reverse osmosis operation, the company is trying to expand their business with the semiconductor industry. Korea is famous for semiconductor industry, but at the same time, they have high amount of the wastewater. So, but based on my studies before, for the semiconductor industry, when they have a wastewater, there are some low molecular weight organic compound. And this should be removed when they utilize it again for the feed water of the semiconductor industry. But the problem is those low molecular weight organic compound has relatively low rejection rate, especially like the methanol, ethanol, and urea has relatively low rejection rate. But at the same time, this process has like the UV at the rear processes. So methanol and ethanol can be removed, but urea is rarely removed with both RO and UV. So for the practical industrial application for the high recovery, we need to focus more on the permeate monitoring for removing those micropollutants. And with this study, and I further move on to the scaling mechanism of the high recovery RO. And this study is conducted for better understanding of the fouling mechanism, because when we use the water from the industry, there might be some content of the divalent ion like the calcium and sulfate. So this will form scaling when there's a concentration high during the concentration processes. So my goal was to know about the main mechanism for this scaling. So this is like the data I generated this week, and like with the data analysis, and the membrane performance degradation is complicated related with the variables. And based on my understanding, the concentration related variables like the concentration factor or the scaling index can be related with this performance degradation. And I couldn't find the reason for the improvement of the performance in this stage, but this is the further investigation topic. But based on this analysis, maybe the concentration has a high correlation between the membrane degradation, but the impact is uncertain because generally the micropollutant concentration is very low. So maybe they might not affect the scaling. Also, I try to understand what is the main influencing factor for the performance degradation. It's not a feed condition actually. It was more like the flow condition. So maybe the flow condition will determine this membrane degradation rather than the feed condition. So micropollutant is more like the feed condition and concentration. So maybe for the fouling formation of this membrane, micropollutant might not have a significant impact. And now also optimize these like the high recovery reverse osmosis process. But what I found is there is a limitation of the design variables for the micropollutant control and permeate quality. So for the better application of the RO for the micropollutant control, we need more model to predict and control those micropollutants. So I summarize our consideration point, and we can consider this point for our future research. So for the energy efficiency, their key interest is high recovery and low SCC. That's their interest point. And micropollutants, not considering SCC optimization because they are like the effect is minimum. And they have a limited SCC impact from micropollutant present. What about the permeate quality? That will be our focus, maybe. But still, they have a limited attention to micropollutant, and they have a lack of real-time monitoring that's missing. And potential increase in micropermeation during the concentration processes. So we can consider how to treat those high concentrate permeate. And also we need the permeate monitoring in industrial and portable application because that might increase the risk. And but still, we also are not sure about the impact of the micropollutant because they are in low concentration. And for the membrane fouling and scaling, micropollutants may affect the fouling and scaling, but as we investigated, maybe the flow condition can be the main source for those like the fouling and scaling in the concentration processes. And for the better practical design and operation, we should focus on those permeate quality and micropollutant control so that we can understand the phenomena better and better application. So that's the end of my talk, and thank you very much for your great attention.
Thank you. And our next talk is